there's a magnetic field around a magnet, and as this moves, then that cuts through the coil lines. In other words, the coil receives lines of magnetic flux cutting through it. And according to Faraday's law, that induces a potential difference across the coil. The direction of the induced potential difference is determined by, or is described by Lenz's law. And that says that the induced current, induced potential difference, is such that it sets up its own magnetic field to oppose the change brought about by the moving magnet. So if we have a north pole approaching this coil, then this coil is going to set up a magnetic field such that there's a north pole over here repelling that north pole. And that causes an induction in the coil such that the current flows in the direction shown by my fingers. But when this magnet then exits through the bottom, then we have the south pole of the magnet receding. And so the opposite polarity will be induced because now the bottom tries to pull back the south pole. So it develops a north pole at the bottom to try and attract back the south, which is the opposite of just now. Remember, just now there was a north pole at the top to try to repel away the approaching north. And so because of that, we see the voltmeter reading altering from one side to the other as the magnet is dropped through. Just watch again. And when we turn the magnet around, we find the same effect, but just with the opposite direction.